Okay, so today we're going to look at a few more relationships between angles and arcs formed in circles. Okay, a little bit of review from yesterday. Last time we looked at the angles and arcs that were formed by lines coming from common endpoints. Okay, we saw the diagram there on the left, two tangents coming from a common endpoint. The one in the middle, a tangent and a secant coming from a common endpoint. And of course, the one on the right, two secants coming from a common endpoint. And they all followed the same rule. The measure of the angle in between the two lines was going to equal 1/2 of the difference between the two arcs that were caught in between those two lines. Okay, but there's one other situation that uses this rule as well. Okay, and that is the situation that deals with a tangent and a chord coming from a common endpoint. Okay, a tangent and a chord coming from a common endpoint. And when this happens, it looks significantly different in a diagram. Okay, because the chord is entirely inside of the circle. Tangent's outside, makes contact with the circle in one place. The chord is entirely inside the circle. So there is really only two places that a tangent and a chord can meet up. Okay, and so this is a possible example. Okay? And the rule is actually exactly the same. Okay, the measure of the angle is going to equal 1/2 of the difference of the two arcs. The problem is, or the difference is that there's not two arcs. Okay, so another way of thinking about that is to say that one of the arcs has the measure of like arc AB, whatever it happens to be there, but the other arc doesn't exist. So what's its measurement if it doesn't exist? 0. So there's actually nothing to subtract. Okay, so it's just as simple as saying that the measure of the angle equals 1/2 of the measure of the arc. We've seen something similar to this in our discussion on circles, where the measure of the angle equals 1/2 the measure of the arc. Where else have we seen that rule? Uh-oh. We need to spend a significant amount of time studying, guys. I'm telling you, this chapter is long. There's a lot of stuff in it, and I've strongly suggested on more than one occasion that you study ahead. Okay, do not let this pile up on you and then try to dig it out at the last minute. This is the same rule as it is for inscribed angles. The only real difference between what we're looking at here and an inscribed angle is that this guy doesn't look like an inscribed angle. Yes, it has its vertex on the circle itself, but does it have its endpoints both on the circle? No, it's really only got one endpoint to really be on the circle because the other endpoint follows a tangent away from the circle. Okay, but it does follow the same rule as an inscribed angle does. Okay, now different situation. We talked about a bunch of different line segments that run into our circle yesterday, tangents and secants and combinations of tangents and secants. Okay, but we didn't really spend any time looking at chords. Well, we've already seen one example of how chords can behave inside of the circle on that last one. Okay, but here is one where two chords are going to intersect. Okay? If two chords intersect in a circle, then the vertical angles that are formed have a particular relationship with their arcs. Okay, well, a little bit of vocabulary in there. What does it mean when they say vertical angles? How do you find vertical angles? No, tick marks are for when you have two links that are the same. What's the definition of vertical angles? Hmm. Like 4 months ago when I told us that, yeah, y'all aren't going to learn this one and it's going to haunt you all year long, and here we are. It's like I knew what I was talking about. Vertical angles are angles that are across from each other at an intersection. Okay, those are vertical angles. Okay, and they have the following relationship with their arcs. So here's the situation that's being described. Okay, we have two chords. They are intersecting. At that intersection, we actually have two different sets of vertical angles. One of the sets is marked in this picture. And that set of vertical angles has a relationship with the arcs, okay, that are in between those two chords. And the relationship is this. The measure of angle AED or the measure of angle BEC, those are the two that are marked. It does not matter which one we're talking about because vertical angles are always congruent to each other. And that relationship is going to be that the measure of the angles, either one of the vertical angles, is going to equal, and just like yesterday, it's dealing with the two arcs that are caught in between, but this time it's a sum. Okay, it's an addition problem. Okay, if you remember yesterday, the formula was a difference. It was a subtraction problem. Today it's a sum. Okay, so what we're going to see here is if the intersection between two of our lines is outside the circle, like it was yesterday with the two tangents, the two secants, or a tangent and a secant, if it's outside, then it's a subtraction problem. If the intersection is inside the circle, then it's an addition problem. So we get a sign change right there. And you can probably get away without copying this part down, but please just take notice. Angle AED and angle BEC, was this the only set of vertical angles there was in the picture that we did up here? No, there was also angle AEB and angle DEC down at the bottom, and the exact same relationship holds true for them, that the measure of those guys is going to equal 1/2 of the sum of the arcs that's caught between those chords. Okay, so notice from the first diagram at the top, second diagram at the bottom, when it changes the location of the angles, it also changes the location of the arcs. Okay, at the top, left and right for the angles, left and right for the arcs. Okay, down at the bottom, top and bottom on the angles, the arcs are also top and bottom. So when you shift which angle you're looking at inside of the inside of the circle, it also shifts which arcs you're paying attention to as well. Okay, and just a little stupid way to try to remember. Okay, we've got a whole bunch of situations that use the formula like we did yesterday, where everything is being subtracted. This is the only situation that uses a plus sign rather than a subtraction sign. And I always tell people to try to remember which one uses the plus. Well, you can remember that it's inside the circle. If they intersect inside the circle, that's the one that uses the plus. Or if you look at the chords, yeah, I know it's not perfectly straight up and down like a plus sign, but the two chords intersect and they make kind of a plus, okay, the way they intersect. Okay, so that's the one that gets the plus sign in its formula. Okay, let's look at some examples and see if we can figure out the math. Just like with any other question in geometry, the key to getting the question right is to correctly identify what you've got in the problem. Okay, well, what do we have? Okay, what kind of line segments do we have here? What's this guy called going across here? What's this guy called at the bottom? It's a tangent. Okay, it's a tangent. Vocabulary, need to learn to speak the language. And this guy coming across here, AB, what's he? Chord. Okay, so we have a tangent and a chord. Okay, and they are intersecting. Okay, when this happens, the rule is to treat this situation much the same as we treat an inscribed angle. And the relationship between the angle and the arc with an inscribed angle is that the measure of the angle is going to be half as big as the measure of the arc. Okay, so let's plug in what we know, see what we can figure out. Okay, we're supposed to find the measure of angle CBA. Okay, that is that guy in there. Okay, so that's obviously what we're looking for, so that's unknown. 1/2 is part of the formula, so there it sits. and the measure of the arc is 126 degrees. Okay. So in order to solve the problem, all we have to know is what is half of 126 degrees. Half of 12 is 6. Half of 6 is 3. There you go. Okay. Measure of angle CBA is 63 degrees. All right, let's look at another one. Okay, once again, the key to answering geometry questions correctly is to at least get off on the right foot. Okay, correctly identify what we have in the picture. What is in this picture? We have a chord, yes. We have a tangent, okay. Is chord and this tangent doing anything? They are intersecting at a common endpoint. Okay, so this should be similar to the problem we just worked. When this happens, we're to treat it like an inscribed angle. The measure of the angle is going to equal 1/2 the measure of the arc. Okay, do we know the measure of the angle this time? Yeah, this time it's provided. 105 degrees equals 1/2 is built into the formula, so there it is. And the measure of the arc. Do we know the measure of the arc? Now that's what we're supposed to find. Okay. All right. All we have to do is solve for our variable, x. Okay, how do we get that 1/2 off of that x? Multiply by the reciprocal. That's right, there you go. Multiply by 2 over 1, multiply by 2 over 1. The 2's cancel right there. That'll leave you with just x equals, we have double 105, which is 210. There you go. Okay, so not a difficult concept. Okay, not a difficult formula, not a difficult formula to use. The challenge of it is seeing it in the problem when it happens. All right, let's look at some different situations. All right, well, here we are again. What's in the picture? Chords, intersecting chords. Okay, intersecting chords. And the question is giving us information about a couple of the arc lengths, arc measurements, and asking us about a measurement of an angle. Okay, so when all that happens, we have a formula that goes along with that. And it says the measure of the angle is going to equal 1/2 of the measure of the two arcs in between those chords. And remember that this one is the one that is the plus. It is the sum of the two arcs caught between the chords. Now we're not interested in like yesterday where we're trying to do the large arc minus the smaller arc. The only reason we did that large minus small is we're trying to keep the arc measurements from going negative. We wanted positive arc measurements. Okay, so that's why we did the big one, take away the small one, so we'd end up with a positive number. Okay, today we don't really care which one's which because addition is commutative. It doesn't care which numbers you add up in which order. Okay, so let's see what we have. Okay, the measure of the angle. Do we know what the measure of the angle is? Okay, no, it's what we're looking for, right? And if we knew either one of those measurements that I just marked in the picture, then we would have our answer. Okay, so the measure of the angle is going to be x. The 1/2 is built into the formula. Okay, now what about the arc measurements? Do we have both of these? Yeah, now remember, we're looking for the arcs that are directly out away from the angle. So sometimes that may force you to make an adjustment, and we may see one of those here in a minute, but we do have them. In this case, 106 and 174. Okay. Well, now x is already isolated for us. All we have to do is just clean up the math. X equals 1/2 times 106 plus 174 is 280. And half of 280 is how much? There you go. Your angle measurement at that intersection where x is positioned is 140 degrees. Could we use that measurement to find out any of the angle measurements going on around there? Yeah, we could. We may need to do that. Okay. Let's look at another one. Now, before we dive too deep into the math on this one, let me ask you a question that's a little bit off the beaten path here. These two chords that are intersecting in both of these diagrams, okay, do we have any indication that they are intersecting at the center of the circle? No, there's nothing in the problem that says it. Okay, is it an eyeball test? I mean, can we just look at it and decide that it intersects in the center or not based upon the way that it looks? No, I wouldn't think so. Okay, so be careful on the intersection of chords. Don't assume that you have a central angle, okay, unless you actually do know that you're hitting the center of the circle. And in these cases, even if it looked like it was hitting the center of the circle without some kind of indication that it was a central angle, that our chords were intersecting at the center of the circle, we wouldn't assume that. We wouldn't want to use the central angles rule that says that the central angle and its arc are going to be equal. Okay, but we do have two chords that are intersecting. Okay, we have two chords that are intersecting. Our problem is giving us and asking about arc measurements. We have angle measurements going on at the intersection. It seems pretty clear that this rule that we've learned today is going to be needed in order to figure this problem out. And the rule once again says that the measure of the angle is going to equal 1/2 of the sum of the two arcs. Okay. Let's start plugging in what we know. Okay, the measure of an angle. Okay, do we have the measure of the angle? Well, we have the measure of an angle. Okay, is it the angle that we would like to have? Let's take a look. If these two guys right here and right here are the arcs that we are going to focus on, which it seems pretty clear that they are, right? Because that's where our unknown is at. Okay, then the angles that go with these guys are the ones that are inside there. Do we have that measurement? Now we don't. We don't have that measurement. Okay, but can it be found? We've got this 127 over here. Okay, what do you know about that arc that I just drew in? What happens instead of starting here, instead of stopping right there, what happens if you continue on and come all the way over? Half of a circle, okay, which is 180. And more specifically, that is a linear pair. Remember this vocabulary? Linear pair. Two angles, one there, one there. They share a side, and together they form a straight angle. That's a linear pair, and a linear pair is always supplementary. Okay, so let me erase some of the clutter I just put in the picture. Okay, we have 127. We have an arc that we would like to have the measurement for because we need it to plug into our formula. And by either, as somebody said, thinking of it like a semicircle or thinking of it like a linear pair, in either case, those two angles are going to have to add up to equal 180 degrees. So if we solve for x by subtracting the 127 away, we're going to find that we have 53 degrees that is unaccounted for in that situation. So that means that in our circle, that's a 53, and that's going to be a 53 because of vertical angles. Okay. Now, do we have the correct angle now? Yeah, here's an arc that you're looking at. Here's an arc that you're looking at. We need the angles that are between there. So yes, we have the 53 degrees there. 1/2 is built into the formula. What about the arc measurements? 73 and y. Okay. From here on out, the math ought to feel exactly like it felt last night while you're working your problems. Okay, you have two choices. You can either distribute this 1/2 and then work the problem, or you can remove the 1/2 to the other side of the problem and then work the problem. Personally, I like to remove the 1/2 rather than distributing it onto my y. Okay, so how do I move that 1/2? Yeah, multiply by the reciprocal. 2 over 1, multiply by 2 over 1. 2 in the numerator, 2 in the denominator. That cancels. It gets rid of the fraction, so we're good to go there. So over here on the left, you got 2 times 53. It's 106. That equals 73 plus y. Now we can start solving for y because the parentheses have been eliminated. And the only thing really to do is subtract that 73 away from our y. Y is going to equal 106, take away 73. That is a 33-degree difference. And there is your arc measurement, even though it's drawn obviously not to scale. That does not look like a 33-degree arc, but that's what the math says, so be it. Okay, that's all for this little chunk of information on circles. We are getting close to finishing up the information as far as all the different lengths and arc measurements and things like that, angle measurements. Before long, we're going to shift our focus a little bit. We're going to look at what's called sectors. That'll be our beginning information at the beginning of next week after we finish up with some information tomorrow. It looks at this point like the test is probably going to be somewhere around Wednesday. Okay, so I think Monday will be the last information, and I will probably not spend any class time reviewing any of the other two-dimensional shapes. Remember, the topic of this unit is properties of two-dimensional shapes. Okay, all we are focusing on is the circles. We have done everything else. That means you may need to spend some time on your own rereading some stuff on your triangles, particularly on your quadrilaterals. Okay, because there's all of the two-dimensional shapes are fair game according to the way they named this unit. So again, don't let all this stuff pile up on you if you have not yet begun to study. I can't imagine what you're waiting for. This needs to be happening a little bit each and every day. Okay, but start thinking about a test towards next Wednesday, and you've got an assignment to go with this, so let's get to it.